Howdy, y'all. It's Mr. Russell. I'm going to be starting chapter 7, and I'm not going to be using the camera right now, so let me know what you think, if you like the camera or not. Um, so when we move on to the electromagnetic radiation, it is was this term was discovered in the 1800s, and that's what we really used to discover the waves. We were focusing on the waves, but you guys really know it as the electromagnetic spectrum, as you have gamma rays on the left and radio waves on the right. And the energies are different. These are high energy and these are low energy, and we can only see what we see in the middle, a little tiny sliver, from violet to red. When you think of electromagnetic radiation, I want you to think of light radiation. Electromagnetic is light. So light can be defined in two separate variables that are uh, indirectly related to each other. So the wavelength and the frequency. Wavelength is the distance between the peaks, and the frequency is how often that occurs. So the wavelength is between the peaks and the peaks right here, and the peak to peak, and the peak to peak. So shorter and shorter wavelengths, and the frequency is how many waves it takes per second. So if this was 1 second, it would be 4 times per second, so 4 hertz. That's what that means. Heinrich Hertz came up with this, and it's a good system for measuring frequency. So, like I said, wavelength, symbolized by the Greek letter lambda, and frequency, symbolized by the Greek letter nu, um, can be multiplied together to get the speed of light, that is c, the universal constant c. If the wavelength is short, frequency is high, and vice versa. So they are indirectly related to each other. One will be high, one will be low. The way you tell is by looking at the exponent. If the exponent in scientific notation is a negative number, it is a very small number. Big number, a positive number is a big number. And speed of light is given to you on your AP test on the formula chart, so don't worry about memorizing that. So if we know the wavelength here, we can calculate the frequency just by converting uh, our converting the nanometers to meters. A neat little trick is when you take nanometers, just take the decimal place, move it over twice to the left, and then multiply by 10 to the minus 7. It's a neat little trick, works every time. And we will then be able to calculate the frequency by just taking the speed of light and divided by the wavelength, and we will find our frequency is 5.09 times 10 to the 14th. You may hear some clacking going on in the background. That's my son playing. So here we go. Oh. So before the 1900s, it was thought that matter was only particles and energy was in waves, and those two were separate things. Until a big debate started with Niels Bohr and a whole bunch of other famous guys that won the Nobel Prize, and Albert Einstein. But Max Planck was the person who found out that energy was released in a quantized amount. What he was talking about is that energy can only be gained or lost in an integer multiple of some constant. This constant h here is the constant that he figured out. So they named it Planck's constant, right there. Planck's constant shows up everywhere when you're talking about quantum mechanics. It is a very frequent constant, and it is a very, very tiny number. And its units are joules times seconds. So the equation is E equals NH nu, and where N is some integer, 1, 2, 3, 4, 5, whatever. It needs to be a positive integer though. What it means is that all the energy is actually quantized. We can't have energy in between energy levels, if that makes any sense. I'll give a visual example coming up. So when a lot of people thought that things were continuous, like waves, they thought waves are continuous. Um, but so like, something that was continuous would be like a cello. If the player takes his finger and uses the bow, and then he moves his finger all the way up and back down the fingerboard, it will it will make a continuous kind of sound. It will go all the way up in pitch and all the way down, hitting every single pitch in between. But the quantized um, version is something where, like a piano, where you can only hit these certain keys. You can't hit any key in between. So that's the difference between continuous and quantized. The quantized would be something like a particle. So the thing is that we had proof that light was a particle, and we had proof that light was a wave. So they debated on and on and on for this. Um, and I'll get to that. But another way to see the quantized version is if we have an electron here in the the first energy level. The electron could jump up to the next energy level too, and it could jump back and forth. But it cannot. I'm going to draw what cannot happen. It cannot be in the middle. So that's what I mean by quantized when it comes to chemistry. So we cannot have anywhere in the middle. We can only have somewhere on this line right here. Here's a great question. If I was to calculate the smallest increment of energy, so when I say smallest, you know that it's going to be the integer is going to be 1. And then of a yellow light whose wavelength is 589 nanometers. So if I use Planck's equation, E equals h nu, this is energy times Planck's constant times frequency. So I need to change wavelength to frequency. By doing that, I need to take the speed of light, excuse me, sorry, let me put it all out there. I need to take the speed of light, I'll let the bottom part clear away, the speed of light divided by the wavelength, and will now give me my frequency here. So then I just take Planck's constant times the wavelength to give me my answer, and it will go away. It will be 3.37 times 10 to the minus 19 joule. That's all I have for you guys today. Why is Planck's constant so small? I'd give you a hint. It is very, very simple. And I want you to calculate the energy of one purple photon. Y'all have a good day. Thanks for watching. You guys have a great day.